Hi, welcome. Today we're looking at the Linux networking stack, and specifically, I'm going to try to focus on the IPv4 TCP implementation. Why TCP? Because it's, one of the most, probably the most important connection mechanism, and why IPv4, not IPv6, mainly because a lot of the internet still runs on IPv4. A lot of, for example, home ISPs don't have IPv6 support, and a lot of reasons like that. So at some point we might look at IPv6, but that's not going to happen today. I'm going to try to keep this a little bit shorter because my last two videos were really long unintentionally, and so I'll try to curb that a bit. And I wanted to apologize for getting such a late start the last 2 days. I had optimistically scheduled the streams for 9:30 a.m. and it's now 10:30. The past 2 days we've had a winter storm and that's missed things up. I probably should have mentioned sooner that the times were a little bit aspirational or optimistic until I really get a sense of how I can do this on schedule. So I may back those off from 9:30 to something like 10 or 10:30, but ideally it would be closer to the 9:30 mark. All right, so that's just administrative stuff. So I'm here in the Torvalds Git repo on GitHub, and I'm in the /net/IPv4 directory. I've taken a look at the Linux Torvalds Git repository before. I guess I'll link that video in the notes, and we can see a bunch of stuff. Down below we have UDP and whatever xframe is, maybe xframe, and some IP stuff, and net filter and BP filter. But what I want to look at today is TCP. So I'm going to open up just all of these TCP files. And as I'm doing this, did I get Kong? No, I don't think I did. As I'm doing this, I should mention that I don't know a ton about networking. I know a little bit. There are lots of people who know way more than I do. And I've never really looked at the Linux networking implementation before. I have a vague idea of what TCP is up to, and I'm not sure how much of it I'll really be able to understand. And but I'm gonna guess we'll be able to get a sense of it. This might be the sort of thing where the implementation is low level and wizardy, or it might not. We'll see. Okay, so I'm in TCP.c, which seems like it, based on its name, should be the main entry point into the TCP stack. And we've got this comment. I don't know what inet means in this context, but we got an implementation of the TCP IP protocol suite for the Linux operating system. inet is implemented using the BSD socket interface as the means of communication with the user level. Actually, let's look up inet. Was an electronic trading platform. Other uses. The internet. Okay, does it just mean internet? All right. Okay, so Alan Cox has written a bunch of stuff, and a bunch of other people. I wonder if Alan Cox has a Wikipedia page. Computer programmer. He definitely looks like a wizard. Not like a not like a literal spell casting wizard, but a 1970s-ish, 80s-ish Unix wizard. Okay. I'm guessing this is the same guy. He maintained some TTY stuff as second in command after Linus Torvalds. Okay. After reducing his involvement with Linux to study for an MBA. Okay. He's also involved with GNOME or GNOME. I don't know how to, I've always pronounced it GNOME, but maybe it's supposed to be GNOME, and x.org. Okay. All right. So that's Alan Cox. So there may be some wizardy stuff in here. What else we got? We've got a description of states. This is nice. So these are TCP states. They should be in this TCP, what's it called? Our request for RPF, request for proposals. Let's see if we can just find the TCP standard. RFC, request for comment. Yeah, that's what I meant. Okay, so 1981. Let's see who's on here. Is there an author? There should be an author list, right? By the Information Sciences Institute. I guess that's the author. And sent. Okay, so that literal string is not in the standard, but maybe we can pull up something about the protocol. Okay, elements, model of operation, host environment interfaces, header format, sequence numbers, establishing a connection. I'm not sure where it would be. Maybe we can look up ACK. Yeah, so you can get an ACK. I'm kind of just looking for a table of some sort. Well, we've got the header format. Maybe let's keep that up. Where is this? This is, I'll just grab this string. Maybe it'll give me. Okay. Got this stuff. ACK, urgent, rust, syn, synchronize. Okay. Here's some sequence variables. Okay. I'm not sure that I'm going to find anything especially too interesting, given that we haven't really started yet. So let's look at these enums or states. I'm guessing they kind of correspond to enums. Actually, hang on one second. Okay. All right, so we've got syn sent, when we've sent a connection request, waiting for an ACK. Syn receive, waiting for a connection request. Sent ACK, waiting for a final ACK in three-way handshake. TCP established, when the connection is established. Fin wait, our side is shut down, waiting to complete transmission of remaining buffer data. Maybe that's like half closed. Fin wait 2, all buffer data is sent, waiting for remote to shut down. Closing, time wait, close wait. And these look like they're timeouts. Well, let's see. Time wait is a timeout to catch resent junk before entering closed. It can only be entered from fin wait 2 or closing. Required because the other end may not have gotten our last ACK, causing it to retransmit the data packet, which we ignore. Okay, close wait is the remote side is shut down and is waiting for us to finish writing our data and to shut down to move to the last ACK, TCP last ACK. Out side has shut down. Should be our side has shut down after remote has shut down. Or maybe it does mean outside. Is it possible that it means outside? I think it means our. After remote has shut down, there may still be data in our buffer that we have to finish sending. And TCP closes, the socket is finished. All right. So that's like well, at least the states for the state machine. We don't have all the transition information to reconstruct the state machine, at least conceptually, but we do have some of it here because it kind of tells us when we need to transition, under what conditions. Okay, we're importing a bunch of stuff. All of this looks expected. Mem block, high mem, I guess is something high memory related, cache, error, polling, modules, cryptographic hash, whatever a scatter list is. I guess it's maybe kind of like a sparse list. And BTF, I don't know, but it seems like it might be important. Kind of sounds like it might be a tree of some sort. Wait, should I look it up? Let's see. Oh, I can't do that, can I? BTF type, BPF, hence BTF regardless of which compiler is used. The type debug info to ensure that maybe it's something debug related. I'll try GitHub search, which is somewhere. Nowhere. Well, 1K commits. Fix resolving. Okay. Is it related to BPF? BPF type format, the Linux kernel. The BPF is some sort of type format. The metadata format, which encodes the debug info. Okay. The name BTF was used initially to describe data types. Okay. So it's to debug info, some sort of data type stuff. Great. All right. So back to TCP. All right. What do we got? We've got some defines, some exports. We've got a struct for TCP splice state. I'm not sure what a splice is. We're tracking the current number of TCP sockets. What does a splice state have? It's got a pipe inode info for some pipe. It's got a length. I don't know how a pipe is implemented, but maybe length is kind of like an index into the pipe. It's got some flags, which is, I'm guessing, a bit flags since it's an int. So the int maybe encodes some, each flag is a single bit of the int. All right, so pressure flag, try to collapse. Technical note, it is used by multiple contexts, non-atomically. All of the underscore SK mem schedule is of this nature. Accounting is strict, actions are advisory, and have some latency. Okay, so we've got TCP memory pressure. Read mostly. Okay. That's different from read only. So I guess that's to let us know that this is mostly read, like optimized for reads, but people can also write to it. And that makes sense because if there's memory pressure, you want some thread or whatever to set the flag indicating that there's memory pressure, and then you want and then you want a bunch of threads to read that flag and act accordingly due to that memory pressure. All right. Very cool. All right. What else do we got? TCP leave memory pressure, which is a function. It's a void function. Oh, no, wait. TCP memory pressure is also a function. So we have the flag, and then we have this actual function. We're going to declare a val. If read once TCP memory pressure, I guess read once. I don't know once in what context, but let's not read this repeatedly. I guess anyone who calls TCP memory pressure is going to get the same reading. What I don't understand is like how would that be like reset? So it seems like memory pressure might come and go. So it seems at some point you'd want to clear it. So I guess you do that with leave memory pressure maybe, or maybe leave memory pressure just is like leaving a critical section. I don't know. Okay. Anyway, so val is going to be set to jiffies. And if not val, we're going to decrement val. And then some sort of comp exchange, maybe compare and exchange. TCP memory pressure is 0 val. So check whether TCP memory pressure is 0 and maybe change it. Compare and exchange. I guess this is maybe like an atomic swap of 0 and val, depending on whether they compare the way that you expect them to. And then we're going to call net increment stats, socknet sk, Linux MIB, TCP memory pressures. So I'm guessing this increments some stats. Okay. So this doesn't seem like it does anything other than notify people that there is memory pressure and record some stats maybe. And it does some computation to maybe check that memory pressure is as we expected it. We've also got leave memory pressure, and we're going to call read once again. And instead of comp exchange, we're going to just have what I think is exchange, TCP memory pressure in 0, set that to val, and if val. So if we exchange TCP memory in 0, pressure in 0, and also val is non-zero, that must mean that TCP memory pressure used to be non-zero. And we're going to net add stats, whatever socknet sk is, I guess maybe getting something from the socket for stat recording. Linux MIB TCP memory pressure chrono. I guess maybe this is like a flag telling it chrono, I'm assuming timing or chronology. And we're going to pass it also jiffies to msecs, to milliseconds, jiffies minus val. Okay, so jiffies is a time, I believe. We saw it earlier I think where we saw it was the other kernel video. And it had something to do with clocks or times. And jiffies minus val seems like it's computing a time, the amount of time that it's been under memory pressure, I guess. So val must be a time too. So val is essentially a duration or like a timestamp. And jiffies to milliseconds, I guess, is either recording the absolute time that we left memory pressure or the amount of time, I think more likely the amount of time that we had memory pressure. Just a guess. Okay. We can seconds to retransmit, convert seconds to retransmit based on initial and max timeout. And this probably is something like exponential backoff. Okay, so we'll start at 0. And if we have seconds is more, okay, what are we passing in? We're passing in seconds, timeout, and RTO max. So if seconds is bigger than 0, we're going to set period to timeout. We're going to set res to 1. And while seconds is bigger than period and res is less than 255, then we're going to increment res. So I guess we'll try for 255 times. We'll increment res. We'll left shift thing this timeout, which I'm not sure. So left should be the operator, and then in C style equal means I can assign the result of the left shift to this variable. So I guess that means divide the timeout by 2, essentially, just by like shedding bits off the end. And then if timeout is bigger than RTO max, then timeout is set to RTO max. So yeah, so that's what it means to be a max. And then we're going to increment period by the timeout, and then we're going to return res. Okay. So what did that do? So we're passing it, convert seconds to retransmits based on initial and max timeout. So it's going to return a U8. What is a retransmit? The res is 1 here. It could possibly go up to 255. Is that number of retransmits? I think it's maybe the number of retransmits. All right. Convert retransmits to seconds. So let's see if this is going to do, if this is going to take some number of retransmits and return a bunch of seconds. That's my guess. So we have more than one retransmit left, I guess, is how I'm going to assume it goes until I know otherwise. We'll set the period to the timeout. I guess that's the period between retransmits. And then we're going to decrement retransmit in a while loop. We're going to left shift the timeout by 1. And if timeout is bigger than RTO max, we're going to say timeout is equal to RTO max. And then we're going to take the period, which is equal to the timeout initially, and increment the timeout. And then we're going to return the period. Yeah, so that's not the seconds between timeouts. Sorry, that's not the second between, it's not seconds between retransmits, because I think that's what's supposed to be what timeout is. Instead, maybe it's the total length of time in seconds where we are retransmitting. Okay. We can compute the delivery rate. It's going to take a TCP socket, or rather a pointer to a TCP socket. We're going to read once the rate delivered. We're going to read once rate interval, US. I don't know what US, maybe microseconds. Set rate 64 to 0. And if rate and int v, we're going to compute the rate, including multiplying by cache in microseconds per second. And then we're going to do div, which I assume is divide, and return rate 64. Okay. We've got an address family independent initialization of a TCP stack, TCP sock. Okay. Address family independent. Does address family mean, so the IPv4 space is divided into these address families, right? Is that what it means? Or is there another sense? Is it BGP? Declares neighbors with whom we want to exchange normal IPv4 unicast routes. Yeah, I'm not sure. Some grouping of addresses. Okay. We're going to do a bunch of stuff. We've got some timeout info, min, dlac max. I don't know what dlac is. TCP timeout init. We've got some jiffies clock stuff. There's a bubble in the pipe until at least the first ACK. So I don't know what a bubble means. I guess it's like an air bubble. There's like a lack of whatever fluid we're imagining in the pipe. So TP app limited equals, I forget what tilde 0 U means. But TP, so then rate app limited equals 1. Okay, we're going to set some socket stuff. We're going to write once to the send buffer some stuff, and we're going to write once to the receive buffer some other stuff, or basically the same stuff, except we have wmem, I assume write mem, and here we have read mem. And then we're going to set bit sock support ZC to some flags, and we're going to call sk sockets allocated inc. I guess increment the number, a recording of the number of sockets we've allocated. Right. And we're going to export the symbol TCP init sock. Is that the function we just looked at? Yeah. So I guess they're using these exports to manage visibility. Some transmission timestamp stuff, and I expect we'll see jiffies. We pass it in a socket and some TS flags. And we're going to get the tail of the write queue from the socket. So I don't know what a socket really is. I know there's a standard for Berkeley sockets, but it seems like it, as a struct, it has something like a write queue that we can get the tail of. And we check the flags. and we're checking whether SKB is the null pointer, I guess. And we can get the shared info and TCP, SKB, CB. I don't know exactly what's going on there. And then we're going to call this timestamp function and do some checking. And there's no jiffies. It's all timestamps. All right. So we can check whether TCP stream is readable. We can wait for an event. Yeah, let's check out poll. Note that we don't need to lock the socket, as the upper poll layers take care of normal races between the test and the event, and we don't go look at any of the socket buffers directly. Okay, so we don't need to lock the socket. That's good for efficiency. And why don't we need to lock the socket? Because the upper poll layers, I don't know what the upper layer is polling, but so there's some layer above TCP. Maybe it just means in the layer in the internet stack, or maybe it means something specific to the Linux kernel code base. But the upper poll layers take care of normal races between the test and the event. So the typical sort of race you get is, I guess, you check whether something has happened, and then you take some action. I guess that's what it means by the event, and you want to make sure that there's no gap between the test and the event. Like you don't want to have the test say that something hasn't happened, and then it just immediately happens after you decide to do nothing or whatever. And we don't go look at any of the socket buffers directly. Okay. All right, so TCP poll is going to return a poll T, which is poll type. We're going to give it a file, a socket, and a poll table, or I guess a pointer to a poll table. We'll declare mask as the poll type, which is maybe what we're going to return. Do we return mask? Yeah, we'll eventually return mask. So we're declaring the return value here. We're going to get this socket by peeking into the socket. Okay, we were given a socket with an ET at the end, and we are getting a sock, I guess, which is possibly different from a socket. And what else? Then we get, we're going to call TCP SK on the sock. And that's going to give us a TCP socket. We're going to declare state and not set it to 0 or anything, I guess, because I think we're in standard C, right? We're going to call sock poll wait on the file and the sock and pass in whatever a poll table is. I guess some sort of way of configuring polling behavior, presumably. Then we're going to set, all right, so we're going to poll wait, and maybe this loops until something happens. And then once we know that something has happened, we're going to call inet sk state load. We're going to load the state from the sk, which was the sock and not the socket. And if state is equal to TCP listen, so if we're listening, we're going to return inet sk listen poll of sk. So we're going to call out to this other function, which is, I guess, if we're listening, then are we the server? If we're listening, I think we might be the server, and we're going to return whatever this function is doing. And then if we get down here, then we're not in TCP listen state. And we say socket is not locked. We are protected from async events by poll logic, and correct handling of state changes made by other threads is impossible in any case. And correct handling of state changes made by other threads is impossible in any case. Okay. Let's see. So we trust the poll logic a lot. I hope there are great tests for the poll logic. Since there are there's no code visible protections. It sounds like it's saying like we wrote the logic and we trust that the logic is correct. And anyway, we can't correctly handle any state changes that are made by another thread. I'm not sure why that's the case, but let's assume that's the case. But at any rate, we'll set the mask to 0. We got epoll epoll hop is certainly not done right, but poll doesn't have a notion of hop in just one direction. And for a socket, the read side is more interesting. Okay. Some poll documentation says that epoll hop is incompatible with the epoll out poll WR flags. So somebody should check this all. But careful, it tends to be safer to return too many bits than too few, and you can easily break real applications if you don't tell them that something has hung up. Check me. Check number 1, epoll hop is unmaskable event. And you can see Unix 98 in our fs select.c. It means that after we received end of file, poll always returns immediately, making impossible poll on write in state close wait. One solution is evident. To set epoll hop if and only if shutdown has been made in both directions. Actually, it is interesting to look at how Solaris and DUX solve this dilemma. I would prefer if epoll up were maskable, then we could set it to send shutdown. By the way, examples given in Stevens' books assume exactly this behavior. It explains why epoll up is incompatible with epoll out. Signed ANK. Okay, so I don't know what all that means, but it sounds like there's some snippetiness about epoll hop and whatever made it into the standards and whether that's right. And this is an interesting function, if unlikely. Purge data. I'm curious what the implementation of unlikely looks like, but I don't think I'm going to go digging for it now. All right, so where are we even? So this is TCP. This is the rest of TCP poll. Okay, so I guess we're going to check whether we're going to check some stuff about shutdown mask, TCP closed, epoll hup, receive shutdown, epoll in, and so we're going to do fancier stuff. And I'm not gonna. This seems like we're entering into standards related stuff that I don't know enough about to really learn anything from the code. It probably makes more sense to look at the standard and then come back to it. We've got TCP IO control. It's going to do a switch statement on command. So I guess you package it in a socket and a command. And those commands can be IO, I guess, is input output, I assume, right? S, I don't know. And then, do they all have C? Oh, yeah, C is for control. S, IO control, I and Q, mark, out Q, maybe input Q, mark, out Q, QNSD. Wait, out Q, NSD. And then some error number thing. Error number, IO control command is my guess. All right, let's see if that sounds right. All right, so what I'm guessing is probably input Q. We're going to check if the state is TCP listen. And if so, we're going to return E and val, maybe error and value error. And if it's not TCP listen, we're going to lock the socket fast. And call TCP in queue, which I guess is probably is the input queue, and then we're going to unlock it fast. Cool. And at mark, we'll return an answer, and it's going to read once erg data, maybe urgent data, and something erg sequence and copied sequence. And we're gonna, okay, yeah. So we're going to check whether erg sequence is equal to copied sequence, and that will, I guess, tell us if we're at the mark. Output Q, I assume, is similar. Oh, but we don't have this, whatever the equivalent of TCP in queue. We don't have TCP out queue. But what do we have? We're going to check if it's TCP listen, an error if so. We're going to get the state and shift it. We're going to have the SYN sent and SYN receive stuff. I don't know what TCPF is. Was that part of the original enum? And if this stuff is true, we're going to say the answer is 0. Otherwise, we're going to read from the right sequence, and we're going to subtract from the send UNA and return that. Okay. And I don't think I have any hope of figuring out what out QNSD is. But we're going to return put user answer int user star arg. I don't know what put user is. Maybe that's going to return something to user space. Is this a system call? Maybe somebody has called into the kernel and we're going to enter user space to return it. I don't know. We've got put user. We can push the mark. I'm just going to do some fancy bit stuff with flags and write to the right seek. I'm guessing right sequence. I don't know. Forced push. SKB entail. Mark erg. Sounds like it probably is mark urgent. It takes a TCP socket and some flags. And if the flags, so if the flag, I guess, is non-zero and message oob, maybe out of bounds, we're going to TP send up and we're going to set TP send up to write sequence. Does that mark anything as urgent? It seems like it might just send stuff. I don't know. Okay, so we can check whether TCP should auto cork. It says something on SKB pushed, blah, blah, blah. All right, what else do we got? TCP push. And it takes a socket, some flags, MSS now. I don't know what that means. Non-egal, non-egal, and size goal. We've got write Q tail, mark urge. Let's see. We check flags and message more, or we're checking if force push of TP, in which case we TCP mark push. Then we mark urgent, I guess unconditionally. We check whether TCP should auto cork. And then we do some other stuff, and then we say TCP push pending frame to the socket with the things we passed in, MSS now and non-egal. We can splice data receive, splice read. Okay. So I feel like I've gotten a little bit of a flavor of what's going on. We've got a transmit size goal. Some scheduling stuff. We can build a fragment. It's going to take an SK buff. Do TCP send pages. Send page. Taking a page. Is this like a page of memory? Send page. Let's look up send page. Bounds measured in the units of system page size. If I just oh, I think this is not helpful. Okay. At the top level, TCP send message and TCP send page gather up data either from user space or the page cache. Okay, so I guess it raids the page cache into SKB packets and tack them onto SK write queue. This sounds super useful. I'll read this later. Will it tell me what an SK is? We've got SK write queue, SKB. Here we can see that the TCP socket maintains a doubly linked list of all pending output data packets header by SK write queue. Another TCP socket member SK send head maintains where in the queue the next packet is to be sent. Okay, so we've got a TCP socket. I don't know if these are members of the TCP socket, but somehow TCP socket, I guess, delegates out to the write queue in the send head. The tail of SKB, I guess, is the write queue. And the head is SK. No. I don't know what that is. Outgoing packets have to maintain some TCP specific information per packet. And we use the SKB right arrow CB control block area for this. Cool. Okay, so SKB is socket buffer. Cool. I wonder if we can find out the difference between sock and sock. I don't know. Okay, so back to TCP. Send message fast open. Some locked stuff. Some lock stuff. Receive urgent. We can peek at the send queue. Let's look at the peek behavior, I guess. So we're going to give it a sock, a message header, and a length. And we're going to set the sock buff to, oh no, we're going to create a sock buff. We're going to look at how much stuff we've copied and whether there's an error. We're going to call SKB RB tree walk. Maybe RB tree is red black tree. And we're going to pass it in the SKB, which is presumably what the tree, and then we're going to pass it in the reference to SK right arrow TCP RTX queue is RTX retransmit, and copy some data stuff, and then we're going to call SKB queue walk on SKB right arrow SK right queue and SKB. Okay. We can clean up the receive buffer. Actually, what did I say? RTX is probably read. I don't know. Receive, I meant. Okay, TCP read sock. This routine provides an alternative to TCP receive message for routines that would like to handle copying from SK buffs directly in send file fashion. All right. And an mmap thing. I don't know exactly what it's doing. We can more mmap stuff. Handle leftovers. TCP zero copy VM insert batch. It's going to take a VM area struct, which is probably either virtual memory or a virtual machine. VM insert pages. We've got TCP receive message locked. This routine copies from a sock struct into the user buffer. Let's see if we use return user. Where did that go? We're at 2425. Yeah, that's not what I wanted to do. Can I go back? No. All right, I'll just scroll to the bottom. All right, so let's just close out this file, see if there's anything especially great here. We can enable transmit delay. I wonder if that's mostly for testing. Got node delay. TCP node delay is weaker than TCP cork, so that this option on corked socket is remembered, but it is not activated until cork is cleared. Get info chronostats. Some timestamping stuff. Okay, we've got a big do TCP get sock option. So we can get the socket options. And this is a big switch. That's, I guess, a bunch of implementations of the socket option get stuff. And okay, TCP BPF bypass get socket. So this is BPF stuff. Do TCP get socket has optimized get sock opt implementation to avoid extra socket lock for TCP zero copy receive. All right. MD5 hash. TCP init mem. TCP init. All right. All right. So that's TCP.c. I wonder if there should be a header file, right? But it's not in here, I think. Unless it is. There's no just bare tcp.h. Let's see if they have an include directory that's easy to access. Not there. We have init, include net. Here we go, tcp.h. I just want to see if it's going to define some struct. Okay, I probably should have looked at these header files. So we've got some defined, some constants, like the TCP window, base MMS, probe interval, fast retrans threshold, and some other stuff. TCP SYNAC retries. This is how many retries are done when passive opening a connection. And so this is where all the defaults are set. I'm curious how often they reset these defaults, or if, like, I don't know how much these are tuned. Keep alive time. Pause. I don't know what PAWS is. Some TCP option stuff. Padding, end of options, SAC block, MD5, option lengths. Declare per CPU. Where did that go? So we've got a per CPU FW allocation. We've got a function before that will check, I guess, comparing two 32-bit unsigned ints and worry about wraparound. Here's an optimized version of TCP under memory pressure, which is going to return a bool, and we've inlined it. And we're going to check if mem C group sockets is enabled, and SK mem CG, I guess C group. So if you've enabled C groups, and I guess this is some Boolean that has something to do with their memory C group stuff, then we're going to call mem C group under socket pressure. So we're going to just delegate out to the C group version of this function. Otherwise, we're just going to call read once on the Boolean TCP memory pressure. Okay, simple enough. TCP out of memory, we're going to give it a sock, and we're going to check the wmem queued and check if it's greater than the sock min send buffer, and sk memory allocated sk is bigger than s prot mem limits. Then we're going to return true, otherwise we'll return false. All right, and then here are the here are the implementations of various functions, not implementations, but the signatures for various functions. Keep alive stuff. Okay, so what was I looking for? I was looking for struct socket. We've got 3 matches. Am I at the first one? No, I'm at the 4th one. All right. I guess socket, this must be from like Berkeley sockets, right? Do we import something socket related? Bug k net sock. Let's look at net sock. At least the header file. And actually, while we're here, let's see what other TCP headers we have. We've got TCP states, and that's really it. Okay. So let's find sock.h. Maybe inet sock. Yeah, sock.h. Okay. This must be a big file. It's slowly inching along. All right, well, while you open that, oh, here we go. Okay, so Alan Cox again. Let's see if this is a big file. Yeah, okay. Nearly 3,000 lines of code, 2970 or so. So as a result, GitHub will refuse to search it for sure. Let's see if we can find struct sock. Const struct sock is a function, right? Sock debug. I think I went type def struct, right? Got a spin lock. Oh, here. Okay, we have struct sock and struct proto, struct net. Do you also have struct socket? Struct socket. Struct socket alloc, struct socket socket, and then some inode VFS inode stuff. Let's see. Is struct socket a function? No, this is return value of socket I, right? Maybe socket pointer, sock pointer. I'm not sure. I'm not going to dig too much further. But I will see if there's an easily accessible sock pointer. All right, whatever. All right, so here's TCP BBR. Bottleneck bandwidth and RTT congestion control. So this is a congestion control protocol. So basically, I think rate limiting things in a predefined way so that there's not too much congestion on the various pipes. So BBR congestion control computes the sending rate based on the delivery rate or throughput estimated from ACKs. In a nutshell, on each ACK, update our model of the network path. Bottleneck bandwidth is equal to windowed max of delivered over elapsed and 10 round trips. Min round trip time is equal to the windowed min of round trip time in 10 seconds. Okay, windowed max. This is just a max function, I guess, with a window. Maybe like a parameterized max function, or maybe it's just a max of windowed. And anyway, we're going to take the max of 10 round trips and delivered over elapsed. And similarly, we're going to get the min as the min of RTT, the round trip time in 10 seconds. The pacing rate is equal to the pacing gain times the bottleneck bandwidth. I'm not sure how to compute pacing gain, but we compute bottleneck bandwidth here. And the C window, the control window, I guess, is the max of the control wind gain times the bottleneck bandwidth times the min round trip time and 4. I don't know where 4 comes from, but I'm sure there's some computation to show that it's either optimal or at least very good. The core algorithm does not react directly to packet losses or delays. Although BBR may adjust the size of next send per ACK when loss is observed, or adjust the sending rate if it estimates there's a traffic policer in order to keep the drop rate reasonable. Here's a state transition diagram for BBR. So we're going to start up. I guess we might enter drain. And from drain, we can probe BW bandwidth. And when we're in bandwidth, I guess we can continue to probe bandwidth in a loop. or we can move to probing round trip time. And from startup, we can also jump directly this direction to probe bandwidth, or we can go this direction to probe RTT, I guess. A BBR flow starts in startup and ramps up its sending rate quickly. When it estimates the pipe is full, it enters drain to drain the queue. Okay, so drain is drain the queue, like I guess like flush. In steady state, a BBR flow only uses probe BW and probe RTT. So we're going to probe bandwidth and probe round trip time. We're not going to drain. All right. A long-lived BBR flow spends the vast majority of its time remaining repeatedly in probe BW, fully probing and utilizing the pipe's bandwidth in a fair manner, with a small bounded queue. If a flow has been continuously sending for the entire min-RTT window and hasn't seen an RTT sample that matches or decreases its min-RTT estimate for 10 seconds, then it briefly enters probe RTT to cut in flight to a minimum value to reprobe the path's two-way propagation delay. When exiting probe RTT, if we estimated that we reached the full bandwidth of the pipe, then we enter probe BW, otherwise we enter startup to try to fill the pipe. And then there's some citations. All right, so let's look at the last bit again. So if we've been continuously sending for the entire min RTT window, and we haven't seen an RTT sample that matches or decreases our estimate for 10 seconds. So we're sending a bunch of stuff in some window. I don't know how to think about it being a min RTT window, but we're sending some stuff and we're estimating round trip time. Okay. I think we start in probe BW, right? Okay. Anyway, if we haven't seen an RTT sample that matches or decreases our min estimate for 10 seconds. So round trip time is not decreasing, and it's not decreasing, and it's not matching. So it's not so it must be bigger than, right? It's not less than or equal to. So round trip time in 10 seconds, it seems like round trip time is increasing. So that's a bad sign. And then we briefly enter probe RTT to cut in flight. In flight, I guess, meaning the number of requests that we've released into the wild and are on the wire, and we want to minimize those. I'm guessing that's what in flight means. I'm not positive. I sort of flag that that's a guess and not uncertainty. And we're going to cut to a minimum value. So we're going to stop sending packets, right? It seems like RTT time is going up steadily for 10 seconds. So we're going to stop sending packets to reduce the amount of in-flight requests. And then we're going to reprobe the path's two-way propagation delay using probe RTT. And then when we exit probe RTT, if we estimate that we've reached the full bandwidth of the pipe, then we enter probe BW, which is, I think what they said was the steady state. And if we have like even more bandwidth left over, we enter startup and we just try to fill the pipe. Okay. Yeah, so in the steady state, it uses both probe BW and probe RTT. Okay. And then let's look back up here. On each ACK, we update our model of the network path. So we're going to get the bottleneck bandwidth, which is this max of how many have been delivered. I'm guessing delivered means ACKed, acknowledged, over elapsed. So this is like I'm guessing number of ACKed packets per like second elapsed over and 10 round trips. Unless elapsed means like, percent, maybe elapsed means the number we've sent. I don't know. Because we're taking a max, right? We're taking a max, I think. And the unit here is round trips, right? The unit here is not a time. And the unit of delivered is number of packets. It's a count. So this is a count and this is the count. So I'm guessing elapsed must be some sort of count and not a time. Maybe. And then min round trip time is a time, and we're going to just take the min of whatever RTT is in 10 seconds. And I don't know how we measure RTT, but I guess we're just going to We know when the packet was sent. We know when we get it ACK. We're going to subtract them, I assume. All right, so we've got the following modes. This is just an enum of the state machine for the state machine states. And then we've got a big struct. And this is going to be the stuff that we need for the algorithm, plus a bunch of stuff that we need to compute things. So like round trip time count is a count of the packet timed rounds elapsed. Packet timed rounds elapsed. So rounds sounds county. Packet timed sounds timey. So somehow, I don't really know what's going on. Maybe you can find out by looking deeper at the code. We've got a packet conservation, which I nearly read as packet conversation, which would be an interesting variable name, I guess. Okay, so pacing gain is the current gain for setting the pacing rate. Cwind gain, I guess the control window gain is the current gain for setting Cwind. So we saw in the gRPC video that for flow, I think for flow control, we saw that they had a PID controller, which is a proportional integral controller, a standard sort of controller from control engineering, control theory, and they use that for flow control. And I'm not sure why TCP doesn't use just like a standard PID controller, because I peeked at the implementation of the PID controller and it seemed pretty. There was not a whole lot going on in the controller. So I don't know if PID controller performs poorly, or if this BBR stuff, maybe if everyone's using an unknown control algorithm like PID, everyone's doing PID control, then maybe the TCP, the bandwidth of the internet as a whole is unpredictable or has some other bad properties. I don't know what the trade-off is between using this standard algorithm and something like another control algorithm. So I'm curious about that. I don't think I'll find any answer to that. Maybe if you, if somebody watching this has worked in that area, please let me know. Okay, so this pacing stuff. I guess let's just look at one of these functions. I guess let's look at convert a BBR BW in gain factor to a pacing rate. Okay, so how do we get a pacing rate? Well, we're going to pass in a socket a bandwidth estimate, I guess, and gain. But how do we know gain? Let's find out where we compute gain. Gain, I'm guessing, is just a difference. We use a high gain value of 2 over log 2 because it's the smallest pacing gain that will allow a smoothly increasing pacing rate that will double each round trip time and send the same number of packets per RTT that an unpaced, slow-starting Reno or cubic flow would. Okay, I've heard of Reno, and I think I've heard of cubic. Those are like classic TCP flows. So what is this saying? So they've got this gain value of 2 over log 2, which looks computer sciencey. And they believe that, and I'm sure that there's some proof that it's the smallest pacing gain that allows a smoothly increasing pacing rate. So we want the pacing rate to continuously increase, I guess, smoothly, that will double each round trip time and send the same number of packets per round trip time that an unpaced slow starting Reno or cubic flow would. So there's some reason that it's got some optimality property, and that's kind of the default gain. So we've got, right? BBR high gain, BBR drain gain is another constant. The pacing gain of 1 over high gain in BBR drain is calculated to typically drain the queue created in BBR startup in a single round. Okay, so I was curious what gain is, and gain is constants. So these are constants that have nice properties. Okay, so that's BBR. Let's see what else we got. This is the binary increase congestion control for TCP. It's got a home page. We took the implementation from some paper from Infocom in 2004. Unless BIC is enabled and congestion window is large, this behaves the same as the original Reno. So it seems to be some sort of optimization over Reno, which is like an older thingamajiggy, an older control flow algorithm. And this is, I guess, different from Reno and hopefully better than Reno if BIC is enabled, okay? And we have a large congestion window. Okay, we've got a beta scale, a scale factor, beta calculation. The max control window is equal to the send control window times beta. We've got a int for fast convergence, which we're setting to 1. I'm assuming that's not supposed to be just like a Boolean, like whether we should do fast convergence. And we've got parameters, fast convergence, max increment, low window, initial SS thresh, and it's beta for multiplicative increase. Okay. I'm not going to look too much into that. All right, TCP BPF.c. All right, BPF TCP ingress. TCP BPF push. Is BPF the thing I looked at before with the debug stuff? I think there's like ePBF, right? Through BPF. TCP BPF, also known as BPF sock ops, is a new mechanism that supports setting TCP parameters through BPF programs. From Facebook. But what is BPF? What is BPF syntax? Berkeley packet filters. Is that BPF? There's eBPF. Okay, so this is what eBPF is like all the rage. So it's a technology that can run sandbox programs in a privileged context, such as the operating system kernel. It is used to safely and efficiently extend the capabilities of the kernel at runtime without requiring a change to the kernel source code or load kernel modules. And this, I think, is being used by cloudy people that work in the cloud, to do something closer to user mode networking, maybe, is the way to think about it. We can efficiently extend the capabilities of the kernel at runtime without requiring to change the kernel source code or load kernel modules. Safety is provided through an in-kernel verifier which performs static code analysis and rejects programs that crash, hang, or otherwise interfere with the kernel negatively. So there's some check, some static code analysis check, I guess, at admission. And then if you are admitted, then you just run at full speed because the code doesn't change, I guess. But that's not what BPF is. That's eBPF. So BPF is Berkeley packet filter. It's a technology used in certain computing operating systems for programs that need to, among other things, analyze network traffic. It provides a raw interface to data link layers, permitting raw link layer packets to be sent and received. All right. So I think this is also much older, right? From 1992. Okay, so I don't have a good sense of, for example, TCP dump processes may want to receive only packets that initiate a TCP connection. BPF returns only packets that pass the filter that the process supplies. This avoids copying unwanted packets from the operating system kernel to the process, greatly improving performance. So BPF supports filtering packets, allowing a user space process to supply a filter program that specifies which packets it wants to receive. So you can like subscribe to certain packets from user space. And this will do some sort of filtering and give you the packets that you ask for. So that's BPF. All right. Cool. And then there's also the Badminton Players Federation. Okay. So this is some BPF stuff. I guess maybe the implementation. So BPF TCP ingress, we're going to get a socket, a P socket. a socket message, apply bytes, and some flags. And we've got BPF push, which has similar arguments. Push lock, send message reader, something parser. So where does the send verdict? Where's the filter enter in? So we're going to include filter.h. And I don't know what function actually sent, like, presumably you pass it some filter eventually, or, at the start of your operation. And I'm not sure what the filter type looks like. You can rebuild protos. Insert proto ops. BPF clone. I don't know. Okay. So here we are in TCP CDG. This is Kaya delay gradient congestion control. All right. The implementation is based on some papers. Scavenger traffic, less than best effort, should disable coexistence heuristics using parameters, use shadow equals 0, and use inf equals 0. Okay. Less than best effort, scavenger traffic. Never heard of that before. So we've got parameters window, backoff beta, backoff factor are crucial for throughput and delay. Future work is needed to determine better results and to provide guidelines for use in different environments. All right, so more congestion control. See if there's anything especially interesting here. We've got the grad, I'm going to guess, is gradient. Yeah, so here we go, gradients. So we're somehow going to compute gradients and maybe do something like a hill climbing, some sort of optimization using gradients that on the flow control data or the bandwidthy data. All right, TCP Kong. Pluggable TCP congestion control support and new Reno congestion control based on ideas from IO scheduler support and Web 100. Wow, I didn't know there was a Web 100, but it's got to be better than Web 3. So I guess watch out. All right, so we've got a spin lock, a list head. Okay. Simple linear search, don't expect many entries. So we're going to CA find, we're going to do a linear search because we have a small list, and linear search performs well enough on small enough lists, and on super small lists, I think it's often better because of the overhead of other faster searches. And this seems to be some sort of, what do they call it, pluggable? So I'm guessing it's some sort of API to make it easier to handle congestion control. Okay, so we can attach a new congestion control algorithm to the list of available options, TCP register congestion control, and it's gonna take a congestion ops, a TCP congestion ops, and add it to some set we've got a list and we're gonna lock it. And maybe that's the list that we do the linear search over. I guess that would make sense. All right, and we can get the name, we can get the congestion control algorithm by the key, or I guess the name of the algorithm. We can set a default congestion control. All right, so this is for like having multiple options of congestion control and letting users, I guess, choose which one they want per application or per, I don't know, per stream maybe. All right, here's cubic. I think this is maybe in the, this is an older algorithm, I think. Or maybe not, 2008. Okay, so TCP cubic, binary increase congestion control for TCP v2.3. Binary increase. Maybe it increases by powers of 2. Cubic integrates a new slow start algorithm called high start. The details of high start are presented in some paper from 2008. Unless cubic is enabled, and congestion window is large, this behaves the same as the original Reno. So again, a similar thing to Reno. I don't know how this is related to the first thing that was similar to Reno that we saw, but we're going to calculate the cubic root of x using a lookup table, doing Newton-Raphson. Yeah, okay, so interesting. So more Newton-Raphson is a classic Optimization algorithm, root finding algorithm, I think technically. And it's used for numerical analysis. So I guess, similar to the gradient thing, right? Okay. So this is an implement. So here we are in TCP, DCTP, TCP. I'm guessing this is a lot of control algorithms. I'm guessing these are all control algorithms. So I'll kind of jump through them quickly. DC TCP over Reno, an enhancement of the TCP congestion protocol designed for data centers. Okay. High burst tolerance, low latency, high throughput, with commodity shallow buffered switches. And it's described in some paper from 2010. All right. What else do we got? I think that's the header for the for that algorithm we just looked at. We've got TCP fast open. And I don't know what this is doing, but it's got some stuff with ciphers. Get cipher. And you're going to pass it in a key. Is this like resumption? Fast open cookie gen cipher. An incoming SYN or SYNAC frame contains a payload and or a FIN queue, this additional value over FIN. I'm going to actually look up TCP fast open. It seems like this might be like resumption, like you're passing in a cookie. Maybe you have auth data from another call. Is an extension to speed up the opening of successive TCP connections between two endpoints. It works by using a TFO cookie, a TCP option, which is a cryptographic cookie stored on the client and set upon the initial connection with the server. Okay, yeah, exactly. All right. Cool. I don't think I knew that existed. TCP high speed. Sally Floyd's high-speed TCP congestion control. All right. And it's got an RFC attached to it. So more congestion control. HTCP congestion control from 2004. All right. A TCP high block congestion control algorithm from 2004. TCP Illinois congestion control from UIUC. That would be the Illinois part, I guess, from 2007. TCP input, an implementation of the TCP IP protocol suite for the Linux operating system. Wait, what? Didn't you already see that? iNet is implemented using the BSD socket interface. Okay. But what does input mean? We've got slow path, lost retrans, data act. So keeping track of various data. Clean act data disable. BPF skops parse header. I wonder if we get, what was it called? It was called a filter. I don't see filter in here. TCP ACK update RTT, which takes a socket flag, some sequent RTT, SAC RTT, CA RTT RAID sample. Maybe this is a higher level file than TCP.c. It seems like maybe it is. So compute time elapsed between last SYNAC and ACK completing 3 WHS. So I'm seeing a lot of stuff to compute stuff to record like statistics that you would use for things like congestion control. You can restart a timer after forward progress on connection. If we get here, the whole TSO packet has not been ACKed. You can clean the RTX queue, remove acknowledged frames from it is a retransmission. Remove acknowledged frames from the retransmission queue. If our packet is before the ACK sequence, we can discard it as it's confirmed to have arrived at the other end. All right. Cool. And this file is not huge, I guess. TCP con control, the ultimate congestion control function that aims to replace the rigid CWND increase and decrease control, which are these functions. It's called toward the end of the processing an ACK with precise rate information. All transmission or retransmission are delayed afterwards. By ultimate, I'm guessing it means like this is the thing that eventually congestion control stuff. So you're going to call it on a socket, an ACK, I guess maybe the latest ACK. It's around once per ACK. An ACT SACT, which I'm guessing is kind of like programmer humor. Like, I don't know what it means to be sacked, but I'm guessing the rhyming is not a coincidence. I'm going to give it a flag and a rate sample, right? And it's not going to do much. It's going to get the congestion control and I guess delegate out to it. So maybe this is the congestion control file we saw a few minutes ago. And if TCP in control window reduction, we're going to call control window reduction. And if TCP may raise control window, we're going to call TCP congestion avoid. Cool. We can ACK update window, update our send window. TCP OOW rate limit. Return true if we're currently rate limiting out of window ACKs and thus shouldn't send a do back right now. Okay. And now here's TCP IPv4.c. This is the same, I guess, comment. The code is split from TCP.c and TCP input.c and TCP output.c. Linux bottom half. I don't know what that is. Okay. We're going to define some stuff per CPU. Sorry, what is this called? IPv4. What makes this IPv4? So this is split out from other files is what it said. So v4 connect. Yeah, so I'm guessing that this is the stuff that has addresses. So v4 connect, this will initiate an outgoing connection. v4 MTU reduce. This routine reacts to ICMP frag needed MTU indications as defined in this RFC. It can be called through TCP release CB if socket was owned by user at the time TCP v4 error was called to handle ICMP messages. So we can change the MTU RTO revert, and we can call an error function. TCP v4 send check. Yep. So this is, I guess, like establishing connections, IPv4 stuff. The code following below, sending ACKs and SYN receive and time wait states outside socket context is ugly. Certainly. What can I do? I don't know if it performs well and it's maintainable. I guess there's nothing really to be done about ugly code. You could try to prettify it, but you know, in the Linux TCP stack, there might be other overriding concerns. Okay, so TCP low priority. Low priority is a distributed algorithm whose goal is to utilize only the excess network bandwidth as compared to fair share or bandwidth as targeted by TCP. So this is like, maybe this is similar to scavenger traffic. So it's kind of leftover traffic and we're trying to use the rest of it for low priority traffic, I guess. All right, TCP metrics. This is going to be metric stuff. And we saw some stuff where it was recording mini socks. An implementation of the TCP IP protocol suite. Oh, yeah. But what is mini socks? I'm not sure. And I'm not really I guess I don't care enough to really find out. All right, TCP NV is TCP with congestion avoidance. It's the successor to TCP Vegas that has been developed to deal with the issues that occur in modern networks. Like TCP Vegas, TCP NV, maybe New Vegas, supports true congestion avoidance, the ability to detect congestion before packet losses occur. When congestion, I guess, as operationalized as queue buildup starts to occur, TCP-NV predicts what the control window size should be for the current throughput and reduces the control window proportionally to the difference between the current control window and the predicted control window. Okay, so more control flow stuff. TCP offload. This is TCP offloading stuff. I guess let's not look at that too much right now. TCP output. We saw TCP input. I'm guessing this is just the dual to the input. It's going to handle the transmission side. TCP write transmit. Whether it's an acceptable sequence, advertise MSS. What is MSS? Calculate MSS to advertise in SYN segment. Yeah, I don't know. MTU? Is it something related to MTU size? Confused by large MSS. I don't know. Okay, some data send stuff. Yeah, so this is just the dual to input, it looks like. TCP rate. The bandwidth estimator estimates the rate at which the network can currently deliver outbound data packets for this flow. At a high level, it operates by taking a delivery rate sample for each ACK. The rate sample records blah, blah, blah. So I wonder if this code is used by all of the rate control stuff. So we're just estimating rate stuff. When an SKB is sacked or ACKed, we fill the rate sample with the prior delivery information when the SKB was last transmitted. If an ACK sacks multiple SKBs, sacks or ACKs, e.g. stretched ACKs, this function is called multiple times. And it's called TCP rate SKB delivered. All right. TCP rate gen, update the connection delivery information to generate a rate sample. All right, so let's close as much as we can. TCP recovery. Okay. Rack loss detection marks a packet lost. So I guess we're checking if things are lost, and then we'll try to retransmit. We have RTX. Yeah. New Reno mark lost. Okay, some of it might be new Reno specific. TCP scalable. Tom Kelly's scalable TCP. All right, some sort of optimization, maybe also flow control related. TCP timer, an implementation. No. Clamp RTO to user timeout. So these look like timer helper functions, write error. TCP out of resources. Orphan retries. Okay. Let's see. TCP ULP. Pluggable TCP upper layer protocol support. Don't know what that means. Register ULP. Attach a new upper layer protocol to the list. Yeah. Okay. I don't know what an upper layer protocol is, but maybe it's something is in the standard. TCP Vegas. This is going to be the Vegas control algorithm. And that's the header for the Vegas algorithm. Vino is the Vino control algorithm. Maybe some sort of combination of Vegas and Reno. Right? TCP Westwood, that sounds like another control algorithm. It's an end-to-end bandwidth estimation for TCP. And it employs end-to-end bandwidth measurement to set control window and SS thresh after packet loss. The probing phase is as the original Reno. Cool. TCP, yeah. Yeah, TCP. From this. How much do you want to bet this is a control flow algorithm? Number of packets, queued at the bottleneck, fraction of queue. Yeah, it looks like a control flow algorithm. Doing Reno now. Okay. All right, that's it. So that's a look at TCP. Most of the code is related to flow control, which is not so surprising. But the stuff that's not related to flow control kind of makes sense. It seems pretty similar to what we saw in gRPC. We've got a bunch of queues. We've got send queues and receive queues. And it's all about how you manage those queues. And then there's some kind of learning algorithm that looks at how smoothly your transmission and receiving is going and adjust things based on that. And so that's TCP. Thanks for watching.